Hey everyone, I'm here to talk to you a little bit about binary today. So binary is this language, this system that computers use to translate the actual events that happen in the computer into readable outputs. So readable outputs could include the things that we see on the screen, like all of these nice lines that I'm able to draw. It could include taking those events that happen in the computer and turning them into numbers or into letters. It also means we could take a user's input and turn that into readable events on the computer, or things that can actually happen within the computer. For example, if you press the K key or the A key or the E key, those all mean different things. And so you'd want the computer to react a little bit differently to those presses. But when we write things in a code, it actually takes it one step further, and we say, hey, we've put together this list of instructions for you, the computer, and we want you to follow it in certain ways. So we have these things called types. Now, types are essentially specific data sets that we want to process in a certain way. So these are just pieces of data that have very specific constraints, certain rules that we have to follow when we interpret that data. And it plays a big role on the computer side, because the computer has to know whether to treat a certain type of data like an int or like a string or a bool or a char, because it'll mean different things for your code. Each one of these types has a different function. Each one of these types has a different size. And because of all that, they're not equal. So let's talk a little bit about binary and what it is and why it is, and how that plays a role in each of these types. So first off, we've got the zeros and ones that everybody's familiar with. If you can bear with me for a moment. So we've got a 0 here. Actually, I think I had the brush. There we go. I wanted those nice big strokes. So we got a 0 here, and we got a 1 here, and these will be the basic tools we use to describe binary. For the computer, it's actually a little bit more abstract than that. I guess not abstract. This is more abstract than the computer, but anyway, for the computer, it's harder to understand. There's actually a physical event going on, but we're going to describe it as a 0 or a 1, as a true or false. True would be 1, false would be 0. So in binary, let's start with just translating everything directly into a number, because mathematically that's how people like to think about it. I'm going to create some placeholders here, and each of these placeholders will represent a digit. So we're going to start with the base 10 system, and then we're going to move on to the binary system after that, because I think it'll make more sense. In the base 10 system, we start from right to left, and what we're going to do is we're going to start with the smallest number. We'll call that a 0. And then if you make it just one step bigger, it would become a 1, and then a 2, and then a 3, and then a 4, etc., until you get to a 9. And a 9 is our largest digit in a base 10 system. At that point, if you go one bigger, then what we do is we cycle back to the beginning, and we carry on to the next placeholder, our next biggest digit. So originally what we had was we had a 9, and we had a 0 here. And then because we wanted to increase this past our limit, this goes back to the very first digit, 0, and we added 1 to the one on its left. So this became a 1. And then if we wanted to continue increasing, then this would become a 1, and then a 2, etc., and we'd carry on until eventually we got to the point where we needed to carry on to the third place. Binary is very similar, except instead of using a base 10, we use a base 2. So in a base 10, we have 0, 1, 2, 3, ... all the way up to 9. But in a base 2, we only have 0 and 1. So the difference is, for binary, if we start with the smallest number, we've got zeros here. And then if we make it 1 bigger, then all I need to do is just get rid of that one, delete it, and then make it a 1. But if we wanted to make it 1 bigger than that, we've now run out of digits. So we have to go back to the 0 and carry over to the next side. So we'll make this 1 bigger. So I'll make this, again, a 0. And then I'll make the one to the side of it 1 bigger. So this will be 0, and that one will be a 1. So if I wanted to make this overall number 1 bigger, just like before, I'm going to take the number all the way on the right and increase it by 1. And if I need to carry over, then I'll carry over. So to make this once bigger again, I'll take that number, delete it, make it a 1. And then if I want to make it bigger again, then I would make that a 0, carry over. And watch what happens when I make that a 0 and carry over. So I'll make that a 0. Carry over. So 1 plus 1 in binary, we've now reached our limit and we need to carry over one more time. So I'm actually going to delete this, make that a 0, and carry over. I might sound a little bit repetitive at that point, but the point I'm trying to make is there is a system with rules, and we're using the exact same system as our base 10, except this time we now have a base 2. So to increase the size, we'd again increase that by 1, and then etc., etc. So let's translate these things that I just described, the events I just described, into actual numbers. This number right here is the result of having a 0 here, a 0 there, and a 1 there. The smallest number would have been if I had zeros all the way across. That would be 0. If you increase it by 1, so the number 1 would be represented by a 1 in the far right column. The number 2 would be represented by a 1 right over here and a 0 there. If we increase it again, that makes it a 3, and increasing it again makes it a 4. It's really hard to think about that, especially when numbers get bigger in binary, and they can get pretty big. So we have another trick that we can use. If this was a base 10 system, that would be 100, right? It would be like 10 to the second power. Well, in a binary system, we have a similar trick we can use, except instead of using 10 to a power, we're going to use 2 to a power. So this digit represents 2 to the 0 power. This one represents 2 to the 1 power, and this one represents 2 to the 2 power. So every number in this place would be a multiple of 2 to the 0 power. So currently we have 0 of those. Every digit in this place would be a multiple of 2 to the 1 power. So currently we have 0 of those. And then every digit in this place is a multiple of 2 to the second power. So we have 1 of those. So if you take all of this data and you put it together, we have 2 to the second power plus 2 to the first power plus 2 to the 0 power. Except this one right here is times 1, this one is times 0, and this one is times 0. Since anything times 0 is 0, we can cancel those out, and we're left with 1 times 2 squared, which is just 4. So this number in binary is 4. Alright, so now that we kind of understand how binary works, let's look at a couple of examples of numbers and what they would look like in binary. We're going to attempt to make the number, you know what, before we even make any numbers, let's just read a couple numbers. So I'm going to write it out in this format where everything's all spaced out because I think it makes it a little bit easier to read things. Notice how I'm only using zeros and ones, and by only using zeros and ones, I'm committing to that binary system. If I wanted to read this number and translate it into something that we're used to, then all I need to do is, following that same pattern, write out my powers of 2 and then eventually add them together. So this one would be 2 to the 3rd, here's 2 to the 4th, here's 2 to the 5th, and now I want to add all of these together. Since I don't need the zeros because anything times 0 is 0, I could just cross those off if I really wanted to. So I have a 2 to the 5th plus 2 to the 3rd plus 2 squared plus 2 to the 0, which is just 1. If you know your powers of 2, this is going to go a lot quicker. we've got 32 plus 8 plus 4 plus 1, and that comes out to a total of 45. So this number 01011101 is the binary equivalent for 45. So the question pops up, when it comes to computers, how many digits should we actually go? Like, how many of these numbers should we have in any kind of binary information if we want it to be as efficient as possible? And the answer to that is it really depends on what you're trying to build if you wanted to go for maximum efficiency. But as a standardized practice, we've decided that 8 of these digits is enough. And we call each one of these digits a bit of information, because that's really all it holds. It's just a bit of information. It's a little bit. But if you take those 8 bits and you put them together, then that makes a byte. Now it just so happens that 8 bits would be 8 ones, and that goes all the way up to 2 to the 7th. Now I'm not going to go through the math proof, but if you add up one of each of these, it's going to be the highest power times 2 minus 1, which turns out to be 2 to the 7th times 2 minus 1, that's 255. So this amount of data is the highest number that those 8 bits can create when put together. We call those 8 bits a byte. So a byte is B-Y-T-E, just like that. So if you ever look at your internet speeds and they say you're getting 100 MB, they're talking about 100 megabits per second. And really what that means for you is it's about 12.5 megabytes per second. So if you ever think you're getting gypped because you're only getting 1/8 of what they're promising, it's because they're not actually reporting it in the unit that you're expecting. They're reporting it in bits and you're expecting bytes. Now, how many bytes does it take to represent each type of data? Let's look at some of the examples. So if we had a bool, we'll start with just a bool. A bool is a really simple data type. It only has 2 possible values. Do we really need a whole byte to represent a bool? The answer is no. You could potentially represent a bool with just 1 bit. If you had a single bit, that should be enough, theoretically, to save the data for a bool. But you're going to run into issues if you represent a bool with just 1 bit. For example, how do you know if you're intending on actually reading a bool? There has to be some kind of indicator in the code that says, hey, this is a bool. Just like how in your DNA, if you wanted to read a gene, you have to have some kind of indicator in the DNA that says it's time to read a gene. It would be the same thing with bools. You'd have to have some kind of indicator in the code that says it's time to read a bool. So even though we could technically read it in a bit, that's not enough. For simplicity's sake, because the smallest amount of data that we can read is 1 byte, we store a bool as a single byte, even though technically you could fit like 8 of them in a byte. If we go on to one of our other data types that takes up not too much space, there's a char. A char will need a very minimum of 1 byte. And this goes on to our ASCII encoding system, where there are 255 different possibilities for char codes, I believe. And because there are so many possibilities, a char will take a full byte. I'm actually double checking that right now to see how many things are on the ASCII table. It goes up to 127, which would be 128 possibilities. And then if you extend it with all the other special characters, it does go up to our 255 mark. So a char would need 1 byte to fully represent all of the data that it contains. After bool and char, we've got int. Int is pretty cool because it can contain a lot of numbers, like really, really big numbers. But because it has such big numbers, it actually takes multiple bytes. So an int, a regular int, would be 2 bytes. And then if you did a long int would be 4 bytes. Now what you'll find is in some of our faster systems, ints take 4 bytes regardless. And that's because in terms of speed, the computer can process things a little bit faster if that int is 4 bytes rather than the 2 byte minimum. So if you ever find out that your int is taking up 4 bytes, even though it really doesn't need that much space, don't worry too much about it. It's actually in your favor that the int takes up the extra space. It makes things faster. Same reason why a bool doesn't actually take up a bit. It actually takes up a byte because it makes things a little bit faster. And I did also mention a string. So a string is going to take up a certain number of bytes. Well, this one actually depends because a string can have different lengths. It could be the string cat, and cat only has 3 characters, or it could be the string onomatopoeia. Let me see if I can spell that right. Onomato, and then P-O-E-I-A. So that's a pretty long word, onomatopoeia. I hope I spelled that right. And that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters. So for a string, it's always going to be the number of characters plus 1 in terms of bytes. It'll have a terminator. So this string up here for cat, this would be 4 bytes. And then this string down here for onomatopoeia, since it has 12 characters, it's going to be 13 bytes. So strings have a variable size, and it depends on how many characters there are. So hopefully I introduced the idea of binary. We'll go over it again one more time. If we start from right to left, we're using a base 2 system. So the highest digit you can get is a 1, and then you have to carry over to the next sign. If you were to try and interpret these numbers, the one all the way on the right is 2 to the 0 power, and then 2 to the 1 power, then 2 to the 2 power, etc. Going leftward. You can easily add these up to translate it to a number we're used to. Oh, sorry about that. We take 8 bits to make 1 byte, and so 1 byte can hold up to 255 pieces of information, which, by the way, this is a reason why our colors are from 0 to 255. It has to do with bytes. And then here are some examples of different data types and how much memory they would take up in binary theoretically. Again, this is theoretical, which means if you were to actually look at the memory taken up, ints might take up 4 bytes, for example. Bools take up 1 byte, and strings, even though it could be 4 and 13, this really might show up as 4 and maybe 16, just because that's a perfect power of 2. So what I'll have in the next video is something interesting to do with binary, but I don't know exactly what. I'll see you guys in the next video.